I know a lot of the people watching these videos are computer science students. Rather, that's the perspective they're coming to the class from. If I had to pick the most important thing to take away from a discrete math class for computer science students, it would be how to write proofs, right? How to make those kinds of formal mathematical arguments. If I had to pick a second thing, it would be trees. Trees are, from a computer science perspective, there's something called a data structure, and they are used literally all over the place in computer science. Right? So what are they? Right? A tree is a connected, undirected graph with no circuits. Right? So I've got three examples of those here. The one on the left, that's kind of, I think, the most common way of writing them. You've got kind of a central point at the top, and everything kind of filters down from there. But of course, just like with any graph, the position of the vertices, generally speaking, isn't relevant. So you may see something like the one in the middle here, or even this poor lonely guy over on the right. A single vertex. It's technically connected, and it technically has no circuits. So yeah, that would also meet our definition. So all sorts of things that can be modeled using these trees. I've got two examples here. Really, anything that exists in a hierarchy, a tree is going to be a good choice for modeling it. On the upper left-hand corner here, this is a selection of the different types of errors that you can get in Java and their hierarchy. On the bottom right, that's a section of the Unix file system. Really, any file system could be modified nicely using a tree. Trees are also a great theoretical tool. I'm working on another series of lectures right now in computational geometry. And one of the things we talk about there is something called the art gallery problem. And the idea is if you've got an art gallery, where do you need to position cameras so that the entire gallery is covered, right, by your security system? Well, one of the proofs that I'm working on, you start by triangulating the square footage, and then you build something called the dual. Right? The dual is a tree that's formed by putting a vertex in every triangle and then connecting the vertices whose triangles have a side in common. So I've got some definitions here. I've said this before. Graph theory is very dense in definitions. So if a tree has only one or two vertices, then they're both called terminal vertices. If a tree has at least three vertices, then every vertex of degree 1 is called a terminal vertex. For example, with the graph on the left, that would be these vertices down here. In the middle graph, that would be the ones kind of out here around the edges. And from a poor little lonely vertex over there, well, it only has one. So that one also gets to be a terminal vertex. Those are also sometimes called leaves. Interval vertices or branch vertices, those are all the others. Right? So in the left-hand graph, that would be this group. The middle one would be these vertices here. And there aren't any. And that little isolated guy on the end. Okay, so I want you to hold on to those definitions. And in the next slide, we're going to look at a couple of theorems that show some of the properties of trees.